Hello, this is my second video for today. This is my third take for this one problem. We're solving the first and easiest problem, I think. But let me give a quick intro, okay? I want to get better at math and physics. I'm solving a bunch more problems. Maybe these problems are actually some of the hardest because it's a mathematics competition and I have no math competition background. But that's not stopping me, and it shouldn't stop you, okay? That's first. I love math. That's kind of where I got my physics background. I'm a sophomore studying physics again. I'm in my fall semester right now. Whatever. In my physics and math videos in general, I try to break things down as simply as possible to just so everyone can understand what I'm trying to say. Okay. That being said, I also can't walk through every tiny thing, okay? So I'm not doing anything fancy here or nothing too fancy. But if you're not used to proofs, maybe I'm gonna try to solve this problem as as simply as I can. Maybe introduce you to new topics a bit, and at the end you should definitely stick around so maybe I can give more commentary on how to go about doing things like these on your own maybe. And because I've been in your shoes, it sucks not being able to understand even how to do one problem, and the easiest problem. So I hope I can help you with that, okay? Pause the video, read it, maybe you already have. Anyway, let's just get started. So we have a set of real numbers, okay? So we have what? So we have 0, and then we have infinity. I know infinity is not a number, okay? Don't burn me in the chat. Okay, so we have this, and it's closed on a multiplication, okay? Being closed on a multiplication means, a times any number times any other number is also going to be in that set, okay? So, 1 times -1 is also part of this like interval, okay? Of course, that's obvious, but it's a fancy word. So let T and U be disjoint subsets of S. Well, that means that, I'll write that down here. This is S, T, and U. So T and U share no elements. So imagine like two different intervals, basically, like maybe 0 to infinity, and then 0, negative infinity. Okay, so two different intervals. And I didn't mention what sets are, subsets. They're just a collection of objects, okay? Now that's the abstract one. That's the abstract definition. Usually we just do subsets of what? Subsets of numbers or sets of numbers or mathematical things like that, okay? Cool thing though, if we can have a set of like anything basically, and sometimes we mathematically represent those things or whatever. So maybe that's something to think about as far as your curiosity and look more into. Anyway, so we have our set, and now that they said that we have to show that either T or U is closed on a multiplication, because we don't know that now. But so one of the first things you should probably do when you do proofs is convince yourself that something is true. Now this is obviously true. We're working with real numbers, a set of real numbers. It has to be true. In fact, they both have to be closed. Is that right? I'm pretty sure that's right. I don't know why I'm second guessing myself. Like they would both have to be closed because they're both subsets of real numbers. Yeah. Okay. So I think there might be a way to do this proof by direct proof, a direct proof, but it's simpler to do a proof by contradiction. A proof by contradiction means we're going to assume the opposite. So we're going to suppose that T and U are not closed, okay? So that means that if we have two elements in U and we multiply them, they're not in U. By that logic, they have to be in T, right? Similar idea, T1 and T2 are in T, but T1 and T2 times T2 are not in T. They must be in U then, right? Well, now let's look at another element. Let's look at U1 times U2 times T1 times T2. Well, this is where we're going to use the fact that given that any product of any three elements of T is in T, and that the same applies to you. Well, what set is this in? So elements of U, 1, 2, and then 3, right? So this is in U. But if you think about it, this big element is in T, and these two are obviously in T. So no, it has to be in T. And so this is a contradiction. This can't be. It has to be in one set or the other. They're disjoint subsets. They do not share elements. Yeah, so contradiction reached. What? Some people like to do this to show that the proof is finished. And yeah, that's it. Okay, so I think that's it. It's a simple proof. If you want me to say more, please stick around. Otherwise, just please like the video, subscribe, share it with someone who doesn't know about the Putnam, okay? Because it's really cool. It's a really cool competition, okay? Anyway, for those who want the proofs, I suggest what? There's this book called Proofs and Fundamentals. It was originally published in 2000. You can find a PDF online, I'm sure. It's a bit of a long book, but it covers roughly my first introductory proofs class. I love that class. I got a C+. I did bad on the final because long story short, I misinterpreted how much work he wanted me to show for one of the questions, and that cost me a lot of points, needless to say. But it was like a simple enough, topic that I thought I could get it. But whatever. I still love that professor. I learned a lot from him. I still try to go to his lectures and learn from him. Anyway, read this book. I think it will help you. Let me actually do another proof. And a simpler proof. Let me talk about what, proving something. It's logic. There's no other way around it. It's true. Like we're not guessing when we do math, right? We know 1 + 1 is 2, and that's not a proof, or maybe it is. It's an axiom, okay? We have an axiom. We know that integers or natural numbers, they're closed under addition, okay? Anyway, let's show that what? Let's show that two even numbers multiply to two even numbers, okay? Let's do the square. So let's say we have an even number. So a, let's say equals to n. Let's say n belongs to the integers, right? Integers are typically denoted by z. Okay. So let's say we square a. Well, if we square a, we can say that a is 4n squared. If this is true, then maybe we can rewrite it as this. 2 times 2n squared. Okay. And, obviously this right here, or this, is the definition of an even number, right? We have an integer, because we know integers are what? They're probably also close to multiplication, are they? An integer times an integer is an integer. Yes? So this is an integer. This isn't like an even number. Obviously 2 is an even number, or it's even the definition of an even number. So boom. This is a rough scratch of a proof. But the other thing with proofs is what they follow logic. They follow strategies. Like a direct proof. This was a direct proof, right? We took a to be an even number, and then we showed by some mathematical processes that it was even. And so we have assumptions, we have strategies, we have types, and we have objects, and we have a bunch of different axioms sometimes that we're working with, and this is the essence of a proof. Like maybe especially the set theory proofs. I'll do another proof some other time, maybe, or I'll do other proofs randomly in this channel. But set theory proofs usually go along the lines of what? Like, like what? Like let's say we have a big set S and we have a subset T or whatever, and we want to show that every element, in I don't even want to that. Let's say we want to show that there exists an element in S that's not in T or whatever. Well, what okay, like we might just take a random element, say S1 in S is in S, right? If what T was equal to, maybe if T was equal to S, if these sets were equal, then S1 would be in T, but it's obviously not, or whatever. Like maybe this isn't even a proof. I don't know if this is a proof, but they follow steps in logic, and you have to carry each bit of the logic. You can't leave anything ambiguous, and you're communicating your proof too. So you have to have words in your proof. My professor literally told me this. Okay, so your steps need to be clear. Maybe you're not doing fancy simplifications. Maybe you should be clear what you're doing. And yes, all this to say, I want to impart what the essence of a proof is and how important it actually is. I think I probably did a podcast episode on this too. You might want to go check it out, or go check out a video on proofs. And maybe I'll make one. And I think I have one actually. But they're really, really cool. It's really, really important, I think, to challenge your understanding of things. So yes, this is my first Putnam problem. And yeah, hopefully I can do more.